believe it is 5 p.m.
Yes.
That's
Right.
when our speaker is supposed to begin. Today, our first speaker, let me move this out of the way here, is Professor Mehsin Atteya. Mehsin Jabel Atteya from the Mustansiriyah University in Baghdad. And the title of his talk is When Multiplicative Generalized Lambda-Lambda Derivations Supply Commutative Ideals over Associative Rings. So I turn it over to you, Professor Atteya.
Yes. Thank you so much. First of all, I would like to say thank you so much for this organizers of this conference to give me this great opportunity to meet you. Actually, today I am so happy to present my presentation, which is under the title When Multiplicative Generalized Lambda-Lambda Derivations Supply Commutative Ideals over Associative Rings. Okay. In this work, we investigated the behavior of certain differential identities involving three multiplicative generalized lambda-lambda derivations on ideals of semiprime rings. Here, our aim to prove that a ring R has a commutative ideal with the help of the triples F, F, and G with a small g, and H with a small h, are multiplicative generalized lambda-lambda derivation on ideals in prime rings with some conditions. Okay. And the next slide, we find some historical information about this subject. The modern definition of abstract ring appeared in 1914, while investigation reversible rings, which represent the generalized of the reduced ring, it has meaning in the ring theory. In fact, ring theory has undergone a revolution in the recent years with the development of what you know as e-reversible rings. Indeed, there are several authors interested in this algebraic area. Derivations that can be completely determined by the local action on some subset of algebra have attracted attention of many researchers. And this manuscript R acts as a semi-rings, U a non-zero ideal of R, lambda acts as automorphism mapping over R, and the triple brackets are multiplicative generalized lambda-lambda derivation of R. Hence, we investigated the behavior of the certain differential identity involving the three multiplicative generalized lambda-lambda derivation on ideals on prime and semiprime rings. We assume that R is an associative ring with the Z that represents the center of a ring, named that R is a prime ring when R satisfies the expression R1 equals 0, which implies that which tells that R1 equals 0, and R is the prime if R2 equals 0, which supply two options. They are either R1 equals 0 or R2 equals 0. A factual information about the connection between the previous concepts of prime and semiprime rings. Every prime is semiprime rings, but the converse is not true general. For any xy, any two elements xy in the ring, the simple bracket represents the Lie commutator, right by this way, xy minus yx, and the Jordan bracket x circle y equal xy plus yx. The commutativity of prime rings with the derivation was initiated by Posner and specific in 1957. An additive mapping D from R to R is called the derivation if d of xy equal d of x y plus x d of y for all xy belong to R. A derivation is said to be inner derivation if there exists a fixed element A in R such that d of x equal bracket A x for x in R. Over the last several years, a number of authors studied the commutative theorems for prime admitting automorphism or derivation on appropriate subsets of R. References 1 refer to the Mata browser introducing the definition of generalized derivation as following. F, additive mapping from R to R, R here associative ring, is an additive mapping with uniquely determined by a derivation D such that f of xy equal f of xy plus x d of y. D here acts as a derivation. I mean D satisfy this relation for all xy numbers of R. Obviously, every derivation is generalized derivation. Generalized derivation have been primarily studied on operator algebras. In references to the concept of multiplicative derivation was defined by Dive, but forward by Mortendal in references 3. D from R to R is called multiplicative derivation if d of xy equal d of xy plus x d of y holds for all xy in R. Maybe somebody now say this is definition of Martindale. It's look like the definition in the second line. In fact, the differences between them and this and the multiplicative generalized derivation, D here is not necessary additive map. In this article, we generalize the concept of multiplicative. We will generalize this definition, multiplicative generalized derivation to multiplicative generalized lambda derivation. As follows, this is the definition. A mapping of f from R to R, not necessarily additive, is called a multiplicative lambda derivation if there exists a map lambda from R to R such that this is such that f of x equal f of x lambda y plus lambda x f of y for all xy in R. This is definition of multiplicative lambda of associative ring. The next definition, sorry. Yes, this next definition, this is of multiplicative generalized lambda derivation. Also here, f capital from R to R, not necessarily additive, and f satisfies this relation. D here is lambda, it's multiplicative lambda derivation for all xy in R. One may be observed that the concept of multiplicative generalized derivation include the concept of derivation, generalized derivations, and left multipliers, i.e. f satisfy this. I mean by this formula, left multiplies. In the next slide, we find the main results. We begin our discussion with the following result, lemma. This lemma used in the proof of other theorems. In fact, I can't write the details, all details of my proof, because this is require too much slides and too much time to read that, read my proof step by step. So I just mentioned the main idea of my result. Let R be a semiprime ring and U a non-zero ideal of R. If you circle you belong to center of R, then R is commutative ring. Again, I would like mention here, this is U circle U, I mean Jordan product. Theorem 3.2, let R be a semiprime ring and U a non-zero ideal of R, lambda an automorphism on R, and the triple F with F small, G with G small, and H with H small are multiplicative generalized lambda derivation such that H of Z, H of center, is not equal 0 if f of x g of y plus h h of xy minus plus lambda yx belong to z. Here I take the generalized multiplicative generalized lambda derivation, or I mean f and g and h capital word, and lambda is automorphism mapping here. This relation belong to Z, or this the second relation here belong to Z for all x, y, and r. Then R has a commutative idea. Corollary proceed on the previous theorem. I mean theorem 3.2. I can harvest the following corollary 3 by 3. Let R be a prime ring and U a non-zero ideal. Lambda is automorphism on R, and also we have the triple of multiplicative generalized lambda derivation such that H of Z and F and G not equal 0 if the relation of x, g of y plus h xy minus plus lambda of yz of y of yx belong to z, or the second or this relation. Then I get here the ideal subset of the center. I mean the ideal here is central ideal. In theorem 5, 3.5, let R be semiprime ring, U also a non-zero ideal, lambda automorphism 2. And in this theorem, I just used two multiplicative generalized lambda, which they F with F and H with H, such that F small, I mean here multiplicative derivation, lambda multiplicative lambda derivation, non-zero, and H here be a lambda multiplicative left multiplier of R if of x circle y plus h circle y equals 0 for all xy, and this result belong to the ideal, then R has a commutative ideal too. Theorem, in theorem 3.6, R, let R be a semiprime ring, U on a zero ideal of R, lambda and automorphism on R, and the couple multiplicative generalized lambda derivation, I mean F with F small and H with H small, such that F is non-zero and H be a lambda multiplicative left multiplier of R. If this relation in this case belong, not equal 0, belong to Z, belong to the center of R for all xy and ideal, then R has a commutative ideal. Finally, I closed my presentation by the list of some reference, I think it is a good reference, and any person interest and seek for enrich his or him information about the subject in this reference will help him to satisfy that. Thank you so much for your good listening.
I've heard people were applauding. We've got about 10 people in the room who are all listening closely. So, any questions for our speaker? Yeah, so you can identify yourself. So,
Philip Scowcroft, in lemma 3.1, should the conclusion be, or should the hypothesis in the end be, U circle U is contained in the center rather than belongs to the center?
This is theorem 3.2 or sorry,
3.1.
3.2. Yes, yes. This belong to Z. Yes, this is belong to Z. Belong to center. U circle U. I mean U times U plus U times U. The result of them belong to Z, center of the semiprime ring.
Right.
And in this case, I will get R as a commutative ring.
I see.
Sorry. When my ring is commutative, I mean ideal is commutative.
Yes, I was just thinking that U circle U would be the set of all Jordan products of elements of U. Is that correct?
Sorry, but my could you repeat your question?
stand a little closer. There. Yeah, now you can see. Yeah, that's good. Yeah.
Yes, my question was, I thought U circle U would be the set of all X
Yes.
circle Y, where X is in U and Y is in U. And so when you say U circle U belongs to Z, do you mean that all those X circle Ys are in the center?
Yes, yes.
Yes, okay, fine. That's what I want to know. Thank you.
Okay, thank you. Sorry, because your voice is not careful.
Another question? Well, I guess I'll get in the camera here too. Thank you very much. I think that's it. So let's thank our speaker again.